Hello and welcome. In this video, we'll take a look at the gradient computations using backpropagation during the training process for a neural network. Backpropagation is an essential part of the training process and transforms a neural network with randomly initialized weights and biases into a model that matches data. And this video will examine that process. So let's focus on any two connections and their corresponding weights W1 and W2 in a large neural network. For a given value of these weights, we're going to have an output value corresponding to an input. If I change the weights, then the output is also going to change. And if the model output changes, then the error, which measures the discrepancy between the model prediction and the data, is also going to change. So for illustration purposes, let's consider the surface shown in this figure to be the error surface corresponding to those different values of the input weights. The question now is, how do I arrive at an optimal value of these weights, starting off from some randomly initialized starting point? In principle, all we have to do is to descend down the error surface step by step using the gradient function or the slope of the error surface till I reach the minimum. And the minimum on the error surface is going to correspond to the optimal weights of a trained neural network. And I do want to mention that the figure here is an idealized version of an error surface. Typically, these surfaces have multiple maxima and minima and look somewhat like an unmade bed. So I've simplified the illustration by just considering a convex surface. Now what we have to do is to examine what it's going to take to compute the gradient of the error with respect to these model parameters. And for that, let's take a look at an example. So let's consider a simple neural network with one input and two connections to the hidden layer with their corresponding weights and biases. And I'm going to assume that the neurons contain an RELU activation function, although there are several other options. From hidden layer 1, we have connections going out to hidden layer 2 with their own corresponding weights and biases. I'm using a specific notation for this example. The A values denote post-activation outputs of a neuron, and the Z values are pre-activation inputs. The superscripts point to the hidden layers, and the subscripts refer to the individual neurons within each layer. So for a given value of the input, we're going to have an approximation of the target variable, which itself is a function of the weights and the biases, as well as the post-activation values from hidden layer 2. It's important to mention that any neural network is initialized with randomly chosen weights and biases. And our goal is to calibrate this neural network by tuning those model parameters or those weights and biases to minimize the errors or to minimize the discrepancies between the model predictions and the data. And this can be achieved by computing the gradient of the error with respect to the model parameters. So first, let's consider the sensitivity of the error with respect to the weights in one randomly chosen connection to the output. This is going to be given by the derivative of the error with respect to the pre-activation to the output multiplied by the derivative of the pre-activation with respect to the weight. And the corresponding gradient is going to be given by the first expression. Likewise, we can also compute the derivative of the errors with respect to the post-activation values in a previous layer. And we'll soon see that these derivatives are an integral part of the backpropagation process. Now, let's consider the derivative of the error with respect to the weights for a randomly chosen connection between hidden layer 1 and hidden layer 2. This is going to be given by a product of the partial derivatives along the pathway from the output node to the connection containing the weight. And this is going to traverse the post-activation values and the pre-activation values for the neurons along the way. And finally, we end up with a product of four partial derivatives, which might seem like a complicated expression, but if you pause the video right now, you'll see that we have computed the first two terms of this expression previously. And that is nothing but the derivative of the error with respect to the post-activation function in the neuron preceding the connection we're interested in as we move along from the output to the connection. So all that's left for us to address is the remaining two terms in the gradient. The first term is the derivative of the ReLU function, which is what we're using in this example. And the second term is nothing but the post-activation value from a previous layer. Also, since we can, let us also compute the derivative of the error with respect to a post-activation value in layer 1. It's important to note that there are two routes that lead to this neuron from the output. So we're going to start from the output to the pre-activation for the output node, then the post-activation in a preceding node to its pre-activation value, and finally to the post-activation value we're interested in. The next few steps in the video highlight the second pathway leading from the output to the same post-activation value. And if you pause the video now, you'll be able to confirm the expression that you see on the screen. You'll see that the derivative with respect of the error with respect to the post-activation value in a neuron is a function of the error gradients with respect to post-activations in a higher layer or a succeeding layer. Note that there are two terms corresponding to the two pathways that lead to that neuron. Nevertheless, these are quantities that we have computed earlier. Of course, it's important to consider all the paths that lead to this neuron that we're interested in. And so this is a very important concept that makes backpropagation computationally easy to implement. What this expression is telling us is that the gradients with respect to any post-activation value is a function of the gradients along all the ways we can reach a specific neuron, traversing backwards from the output. And these values are conditioned by the derivative of the ReLU function as well as the weights along the pathways. Finally, now, let's see what happens to the gradient of the error with respect to one of the weights from the input node. Again, there are two different pathways through the preceding neuron. So we start from the output node and consider all the post-activation and pre-activation values for the neurons along the way. Since there are two pathways, we are going to be having two terms in the final expression. And because there were so many partial derivatives to consider, we end up with an expression that looks fairly complex. But a closer look will reveal that these contain derivatives that we have calculated in a previous layer. And finally, we get the final form of the gradient with respect to the weight for a connection originating in the input node. So to recap, the process of backpropagation allows us to compute the gradients of the error with respect to any post-activation value. We start by computing the gradients associated with the layer closest to the output. And for inner layers, the gradient of the post-activation value is nothing but a function of the error derivative with respect to post-activation values in higher or succeeding layers. These in turn are going to allow us to compute the gradients of the error with respect to the weights of a neural network. And if we know the gradients, then we can move in directions specified by the gradients down the error surface to reach the minimum of the error surface, which will correspond to the optimal values of the weights for a trained neural network. So a few things that I'd like to point out is that it would be good to pause this video at specific times and ensure that you follow the process. Once you get the concept of backpropagation, you'll see that it's fairly easy to consider gradients in very large neural networks containing tens or hundreds of layers, each containing several different neurons and their corresponding connections with their tunable weights and biases. It's also important to note that this video does not cover biases, but the discussion is very similar and provides for a rapid method to compute the gradients for tuning a neural network. So thanks for watching all the way to the end. Bye-bye.